Every single modern printed circuit board relies on a massive network of dedicated energy storage components to function. These components come in a wide variety of physical form factors, from tiny ceramic squares to larger aluminum cylinders, tailored to specific engineering needs. A capacitor acts somewhat like a battery, but operates on entirely different principles. While a chemical battery holds a much higher volume of total energy, a capacitor deploys its stored charge almost instantaneously. This rapid discharge speed makes them highly dangerous. Casually touching the terminals of a charged capacitor can deliver an immediate, potentially fatal electric shock. To utilize this power safely, we have to look past the protective casing and observe how simply separating electrical charge solves complex problems in signal instability. We will trace this mechanic across two distinct scales: micro-level waveform smoothing in logic circuits and macro-level phase alignment on industrial power grids. Without this invisible electrostatic buffer, the stable, continuous power required by logic gates, microprocessors, and grid infrastructure would simply collapse. Internally, the geometry of a standard capacitor relies on precise layering inside an outer protective shell. The core of the component consists of two parallel, highly conductive metal plates, which are traditionally manufactured from aluminum. Between these metal plates sits the dielectric layer, a strict insulating barrier, typically formed from a non-conductive ceramic. When connected to a power source, electrons flood onto the negative plate. Because of the ceramic insulator, they are physically halted. They cannot cross the gap. The accumulation of this negative charge causes dielectric polarization. The internal molecules of the ceramic insulator physically rotate, aligning their positive poles toward the negative plate and their negative poles toward the positive plate. This creates an electric field. The intense attraction between the opposing charges acts as an invisible tether, holding the electrons firmly in place without physical contact. To visualize this process dynamically, we can look at a hydraulic analog, comparing the flow of electrons through a trace to water flowing straight through a pipe. Inserting a capacitor into an electrical circuit acts exactly like adding an open buffer tank to the main fluid line. The tank gradually fills with water while the primary flow continues unabated. As the tank reaches capacity, the accumulated fluid pushes heavily against the internal walls, creating outward mechanical pressure. We map this mechanical pressure directly to electrical voltage. The accumulation of trapped charge on the aluminum plate creates measurable electrical pressure. We define this specific pressure metric as potential difference, the strict voltage gap measured directly between the heavily saturated negative plate and the depleted positive plate. It is strictly the physical separation of these opposing charges that creates the stored potential energy needed to perform future work. We can observe this potential energy in action by wiring a direct current battery source in parallel with a single capacitor and an LED load. When the circuit closes, an initial rush of electrons leaves the battery and packs tightly onto the capacitor. This flow continues until the voltage of the capacitor perfectly matches the voltage of the battery. At this point of equilibrium, the dielectric barrier actively prevents any further electron flow across the gap. The system is fully charged. If we physically sever the connection to the main battery source, the electrostatic charge remains indefinitely trapped on the plate. By establishing a new, uninterrupted circuit path directly to the LED, the trapped electrons finally have a route to seek equilibrium. The resulting discharge is nearly instantaneous. The capacitor releases its entire electrostatic payload faster than the chemical reactions inside a standard battery. This oscilloscope trace visualizes the voltage drop during that rapid discharge event. The data shows an immediate, towering spike in voltage the millisecond the circuit path is opened, followed by a steep, smooth decay curve as the capacitor completely empties. By providing instantaneous, high-speed bridging power, the capacitor acts as the ultimate localized backup supply for sensitive components. This discharge capability directly solves one of the most persistent problems in power conversion, making alternating current usable for delicate logic microchips. Raw AC power constantly reverses direction, which destroys logic components. Engineers route this AC wave through a full bridge rectifier, a configuration of diodes that forcefully flips the negative AC cycles upward into a positive direction. But the rectifier's output is highly flawed. It produces a series of sharp, pulsating peaks, separated by deep voltage gaps. Every time the wave drops into these troughs, the voltage falls completely back to zero. An unprotected logic circuit connected to this supply would rapidly flash on and off. To bridge these gaps, engineers insert a capacitor into a parallel circuit line immediately after the rectifier. As the main waveform hits its peak, the capacitor charges. The moment the supply voltage begins to drop into the zero voltage gap, it automatically discharges its stored energy. This precisely timed release of electrostatic energy fills the troughs, flattening out the erratic electrical peaks into a continuous output. As the cycle repeats, the final waveform is smoothed out, closely approximating the clean, steady direct current provided by a battery. Without this specific mathematical signal stabilization, running modern microprocessors from an alternating current grid would be impossible. We see the exact same principle applied at a much larger engineering scale, moving from circuit boards up to massive municipal power grids. Heavy industrial inductive loads, such as massive induction motors, cooling fans, and HVAC systems, introduce severe inefficiencies into grid infrastructure. This graph illustrates inductive reactance. Because of the magnetic fields required to run these large motors, the system's current waveform gets dragged out of phase, physically lagging behind the voltage waveform. To counteract this, grid engineers deploy massive capacitor banks. These banks inject an artificial, leading phase shift directly into the local grid. This calculated pulse provides the exact opposing force necessary to push the lagging current wave backward, realigning it perfectly with the voltage wave. By continuously manipulating phase alignment in real time, these large-scale capacitors optimize industrial power consumption and prevent localized grid overloads. Whether smoothing a microchip signal or aligning a municipal grid, every capacitor operates within strict mathematical constraints printed directly on its outer casing. The first value is its capacitance, measured in microfarads. This determines the exact volumetric capacity of the component's internal energy storage. The second value is the maximum voltage rating. This specifies the absolute limit of electrical pressure the internal dielectric barrier can withstand before failing. Pushing a circuit past this threshold results in dielectric breakdown. The internal pressure overwhelms the physical casing, leading to explosive component failure. Even when operated well within their limits and physically intact, capacitors require strict handling procedures. They retain lethal electrostatic charges long after the main power is severed. Verifying the decay of this residual charge is a non-negotiable laboratory diagnostic, practiced daily across the industry. The modern protocol is definitive. Before handling any high-capacity board, an engineer must safely bridge the terminals with a resistor and strictly use a digital multimeter to confirm the stored voltage has decayed into a harmless millivolt range. Integrating these electrostatic components successfully requires a deep working respect for both their mathematical limits and the strict verification procedures that keep them stable.